The next concept we're going to introduce will be the concept of direction angles and direction cosines. So suppose that we are in the three-dimensional coordinate system and we have a vector that points, wherever. We'll put the initial point at the origin and the terminal point wherever we feel like it. Now, given that this has its initial point at the origin and is pointing in some direction, there are going to be three different angles that it creates with the three coordinate axes. These three angles are referred to as direction angles. So it creates an angle with the x-axis, it creates an angle with the y-axis, and it also creates an angle with the z-axis. These are known as direction angles. We're going to label them as the first three Greek letters, or first three letters of the Greek alphabet. So alpha is going to be the angle created between vector and the x-axis. X-axis. So this angle right here would be referring to alpha. Beta is going to be the angle created between the vector and this one will be the y-axis. So this one right here would be beta. And finally, gamma is going to be the angle created between the vector and the z-axis. So this one right up here would be the angle gamma. Now the way that we're going to calculate these is we're going to model the x-axis, the y-axis, and the z-axis by using a vector. Now we already know some vectors that are pointed in each of those directions. So what I'm going to do is demonstrate how to do this with alpha. So what we'll use for the x-axis is we'll use a unit vector pointing in that direction. That'll be the vector 1, 0, 0. Or, as we introduced in the last section, we can call that I. Now, according to our dot product formula, we have that the cosine of alpha would be equal to the dot product of our vector with I over the magnitude of our vector times the magnitude of I. So this would be referring to our vector, and let's throw some components in here as well. Let's call it v1, v2, and v3, as is pretty typical for us. Now, when we take the dot product of v with I, that means we're going to do 1 times the first component and 0 times the other two components and add them all together, which is why we're just going to see a v1. We'll also see this divided by the magnitude of v, and the magnitude of I is no longer present because the magnitude of a unit vector is going to be equal to 1. So with that in mind, the cosine of alpha is going to be equal to v1 over the magnitude of v. This expression is known as a direction cosine. I'll explain why in just a moment. Now, if we do a similar argument with the other two axes, we will be able to get that the cosine of beta is equal to, do the same thing, but instead of using I, we'll be using j. That'll get us to v2 divided by the magnitude of v. This is also a direction cosine. And the cosine of gamma, using the unit vector k, will be equal to v3 divided by the magnitude of v. Now, one of the reasons that we refer to these as direction cosines is because normally when we create a unit vector that's pointed in a given direction, we say take a vector and divide by its own magnitude. That means that we would be taking v1, v2, v3, and dividing all three of them by the magnitude of v. Now when I take v1 divided by the magnitude of v, that just gives me the cosine of alpha. That's what we had up here. When I take v2 and divide by the magnitude of v, I would get the cosine of beta. Similarly for v3, we would get that the cosine of gamma will be our third component. Now, because we know this to be a unit vector, we know that the sum of the squares of the three components should be equal to 1. That's the definition of a unit vector, which brings forth this very interesting identity that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma is equal to 1. We refer to these as direction cosines and direction angles due to the fact that we can now decompose a vector into its magnitude and its corresponding directions. In 2 dimensions, we only needed one angle to do this, and that was the angle theta from polar coordinates. However, in 3 dimensions, we're going to need a total of 3 different angles.